unreading procedure and doing funny things. Okay? So, can I have your silence, please? All right. Next class, we will be using the spectrophotometer again. You guys know what that is? Measuring the absorption. What's the goal? The goal is to find the Ka of methyl red. You guys remember what Ka means? Acid dissociation constant is what? The acid. How well does this dissociate, right? Methyl red is an indicator. It's a pH indicator, just like your phenol in water. Okay. We're gonna measure, and most of the acid-base indicators are actually weak acids that will abstract hydrogen off, right? So that's why when you add the sodium hydroxide, you know, you pull out that H plus, you got this color species. That's how you got it. Same thing with methyl red. Methyl red, you're gonna measure the equilibrium constant. You're gonna determine this value for methyl red. Okay? So, well, what's that? Okay. You're gonna use the color to find equilibrium. In Chem 1A, you've decided what is red, is absorbance in what? Green. Remember that color wheel that you had to do? Okay. So what we're gonna do is you're gonna investigate methyl red acid-base indicator. So the methyl red is a red color. And when it's dissociated, like if you add too much base, it will turn yellow. Okay? So this is your Ka. This is not formatted. This is about what you have. Okay. So you're used to this equation, right? You have the initial known concentration of your weak acid. Okay. You're familiar with this type of ice table, right? Are we following this so far? Okay. So you know that it's dissociate, X amount dissociates. So at equilibrium, you will have the known concentration minus X, and then you have H plus dissociated and X dissociated. Seems like it's simple. So how are we going to find X? We're going to take advantage of the fact that HIN is red, and we'll measure the absorbance by HIN. Okay? So Beer's law says the amount of light absorbed is proportional to the concentration. I put it in gray. This is the official extinction coefficient constant, the path length and time concentration is what absorbance is. I don't know why you're not taught that, but anyways, the extinction coefficient is how much the molecule absorbs. Okay. L is the path length where the beam of light goes through that you measure the absorbance. And that's why when we tell you to get the cuvette to go into the spectrophotometer with the B facing you, we're trying to keep that path length constant because if the manufacturer has the spectrophotometer, the cuvette not precisely measured, your path length may vary if you rotate it. So see what I'm saying? That's why we tell you put the blank in, put it in, or a blank out, put the substance in, and put it in. So that when you do one measure after another, your path length is constant. That's why we make you do that. Okay? Then it's proportional to concentration. So the constant has a unit of 1/n. Absorbance is unitless. I'm finding that experimentally people are putting funky units for absorbance. There's no unit for absorbance. Okay? This is a ratio of units. Okay? Okay. So the part one of your experiment is just to see this escape. It's a very qualitative look that if you took a little bit of the indicator and you add base, you change the color and you add acid, you change spectrum red to see this escape. Okay? Very simple, nothing big deal about it. Now part B is the major bulk of your work. You're going to have a graphic with it as well. So each pair, you'll be working in pair. Okay. You're going to check out, the list is in your manual, but I'm going to just enumerate it. You'll have 250 ml. You're going to check out in one pad so that you return all of this at the end of the lab, right? Two 50 ml volumetric flask with stopper, one 10 ml graduate cylinder, one 10 ml pipette, one 5 ml pipette, and a pipette ball. You will return at the end of the lab period because we don't have, it says 80 steps. You have how many? Okay. On a separate check, then you can check out 100, one of 100 ml volumetric flask with stopper. You can check that out separately because they don't like to return things in pieces, right? Whatever's on the pack, they want you to return them all. Okay? So, first thing you're gonna do is clean 125 pounds of plastic. Remember your unknown that you gave us? You can use that plastic, right? Clean and dry it. She says, put it in the oven to dry. It doesn't really, in the past I've seen it done, not as long as you dry it well. Why are you gonna dry that? You're going to get something called the standard solution that is prepared for you. Okay? You'll be working off that to begin. Okay? You're gonna do, remember in Chem 1A, you've done that absorbance plot? You were made to graph on that light. You know, remember you went in the lab and it was dark, and then you had a group work where you would make different solutions, and you were made to absorption with the concentration, remember, and you had a straight line. This is the Beers plot. You have different concentration, and you measure absorbances. Do you remember that? Anybody remember that? Huh? Yeah. Okay. That's what you're going to be doing again. Okay? So you have some solution that it has a concentration that's given to you in your manual as well. Okay? You're going to take, they're going to tell you how much to take, standard, and then you're going to rinse your pipette again, right? Anytime you have a set concentration, you need to, please move down because when I'm going to pass the quiz out, you can't sit back up there. So please move down. I won't bite you. Because after this, I'm going to give you the quiz. Okay. So, you're going to take that 10 ml of the standard solution into a 100 ml volumetric flask. You're going to add 10 ml of 0.1 molar HCl. Now, you might have a 1 molar solution of HCl. You guys know how to do calculations to get 1 molar? If the 0.1 molar may not be prepared for you, it might be even a 1 molar solution. And you have to do the solution. There are 2 of you working on this. Distribute your work so not one person is standing only. If you're really falling asleep, please stand up and shake yourself so you can wake up and know what you're going to do next period. Okay, with eyes closing. Now, note that there's a standard solution. I put it abbreviated SEND. Note that there is a solution A. There are 2 different things. You mix this up, your graph is crazy, your result is awfully crazy. Keep your eyes open, keep your head open, so that you know what you're doing. A lot of people don't make that differentiation, and they come out with very horrid results. Okay? So please stay awake, okay? You're gonna pipette, prepare solution A by pipetting 10 ml of standard solution into that blah, blah, blah. Here's the table. You're gonna take 10 ml of solution. You're gonna take the standard, you're gonna make solution A. From solution A, you're gonna make a different concentration here. Okay? You guys are gonna do a lot of M1B1, M2B2 calculations. Dilution. You following me? Who's lost? Who's lost is not awake. Are we awake? Yes? Maybe? All right. So, the HCl forces all of the yellow to be red. Remember, if I have this equation, okay, if I put in a whole excess of A, right, which way will the direction of the Chapdelaine currently will go? Is it to the product or to the reactant? To the reactant, right? So when you put in the HCl, Okay, this is way in excess. So it forces the concentration of the 10 ml in 100, right, to be all in the red zone. You won't have much of the yellow. There's not much dissociation because you're pushing it all to the left. You following me? So your absorbance measurement will be actually measuring the HIN concentration, because every time you have HIN in solution, it will have some dissociation. So if you push it with the H plus, you will all go to the left. Okay? So it will reflect the concentration of HIN only. That is what you're building with this, so that next time when you go to measure an absorbance, you can figure out what concentration of HIN you have. Following me? So this plot is very important for you to derive the latter part. So you all know, now you're expert, right? All your flasks and stuff, your pipettes are rinsed. Whenever you're going to touch the concentration, you put a little bit in a beaker, you do all the rinsing so that the concentration is constant as you transfer it, not diluted by the wet plastic. Okay? So, you're going to be measuring at a 550 nanometer, your manual would say that. Okay? First zeroing the instrument with DI water. So is DI water 0, 0, is that one of your points on your graph? Does your graph on this require you to start from 0, 0? Okay, if you're falling asleep, you can't see me nodding, so that's how I check. So 4 points, you're going to have 4 points from here, plus 0, 0 for the water. Okay? Once you have the slope of the line, you can measure the absorbance at 550 nanometer on any solution containing it. Find the concentration of HIN. Look at the sheet that you're going to report sheet. It will have a bold letter to say attached sheet to show calculation. I warn you, right? Every time there's a bold letter that says attached sheet for your calculation, you don't have the automatic deductions. Okay, we're trying to see if you follow instructions when you go to work and your boss says do it this way and you don't, then you're in trouble, right? So that's how we're trying to train you that way. Okay. Is it okay for me to move on? Somebody still copying something? Okay. So now you're gonna do part C, you're gonna be doing the measurement to find K. So you will start now, again, look at this, this is from standard solution. So part B, you're going to take standard, make solution A, and then do the solution non A, right? You're going to part C, you're going to start with standard again, the one you get from the okay? So you're going to do this, and you will use the buffer. There will be 3 buffers sitting there, 1, 2, and 3, 25 ml. That will be the one that makes, what is your KA again? HIN. H plus IN. The first step to do the bare summer product, you put in a constant HCl to push it all to this side. Now what we're going to do is we're going to give buffers to give you the H plus concentration that you plug into this. Okay? So you will get 5 ml each of that, and with the 3 different buffers, you're going to measure, complete the 50 ml mark, blah, blah. So the buffers maintain the H plus as a set value. So you're going to look at the bottle, say what pH it is, or what buffer concentration, what buffer pH it is, okay? So what you're doing, what you're doing is, you know the HIN you put in, the independent red you put in, right? And we're used to this table minus X and figuring it out. What you're doing in this case, though, is you're measuring, in the experiment, you're actually measuring what X is. Can you guys see this blue? Should I change the color? Is it visible? No? Okay, let me change the color to something darker. Okay. In this experiment, you're actually measuring HIN. You're gonna take those solutions, you're gonna go measure them, right? So when you get an absorbance, you know how much HIN that it is in there, right? So you can find your X, actually, because why is your HIN at equilibrium? You following me? That's the species that is absorbing, that is present at equilibrium. Because I told you, when I have HIN and I have some acid, there will be some dissociation going on. You following me? Okay? So you need to find the known HIN you put in. It's not all going to remain HIN anymore. Some of them will get divorced, like couples divorce, right? They will dissociate, right? So you need to find it out. Okay, so what you're doing is this. So known minus Y minus the absorbance will be your IN concentration. You following this insanity right now? Okay, so I'm going to give you fake data that you will copy, okay, to know how to process it. So this is the sample calculation. This isn't what you're going to have in your data. Okay, let's say from part B, the Wheeler's law, because you're going to get the slope of this. We've done the slope before in Chem 1A, right? You know how to do that for that slope. So let's pretend my Bierfeld slope has this. Don't forget your unit. UC 67. When I write this over M, it is 1 over M, right? That's your unit. That's your unit, right? Remember the Gibbs plot? I said absorbance is equal to a constant times the concentration, right? This has the unit of 1 over molarity, so that when you cancel the molarity here, I don't have a unit, right? Say it again. The red is not the blue. This one? Absorbance, this one? Slope?
At the very bottom, it's in the light green. The light green.
This guy. I was doing this to show you that what it was, so I'm gonna make them blue. Sorry, but I was just trying to show you the species so that you can follow this. Okay, I'm just putting this as that was the Y. You know that that's the absorbance is the Y already, right? Should I put it? Can I move it up? Or you got the absorbance yet? You got the slope yet? Can I move it down? If you copy this, you know how to process your data. Because you're just going to copy it off. May I move it to the dash line? So this is the fake absorbance number. So with the slope, you can figure it out, right? What the concentration is. Because this C is actually the slope. And I'm going to change this to dark blue. And as you can see, we carry your sig fig to some inordinate amount of sig fig, and then we truncate it down at the end because you get into a better number rather than rounding too early. Your numbers start negating from the true value. Say it again.
So the IN equilibrium.
This one minus this. Okay, sorry. I didn't catch that. Like I said, the IN at equilibrium is your initial minus the absorbance derived concentration. You all awake and understanding this? Okay? So it's a rather simple experiment. It's just paying attention as